No one is to know. Okay, yeah, I did want to make you aware of something which existed, which I think is new this year. It's an online discussion. If we could go to the overhead here. Here is the home page for us. If you go over here, it's a little bit off screen, but it says online discussion. See that?
Sorry?
Huh?
Could you please turn on the other television?
Could I turn on the other television? I don't know if I can or not. Okay, thank you. Thank you for pointing that out. I normally don't check to make sure everything's working. Okay, there's a chat room here and a username and a password. So I haven't played around with this, but it is something which is available to you, brought to you by the Edge people. Okay, let's continue then. With our work. I did want to announce, first of all, homework. It will be posted today. It was not posted last week. It will be posted today. It'll be due a week from today.
Do you just know what it is that you can tell?
Do I know what it is so I can tell you? No, I don't. I actually don't. I don't know if he's posted it on the web yet. Let me see if he's posted it on the web. If we go to assignments and exams, no, I don't see that he's posted it as of yet, so it should be posted. So, huh?
On the board, it says it's now available.
On the board, now available at the class website. Okay, so it is available. It is available. How do we get there?
I think this is not the class website.
This is not the class web. Oh, he was going to post it later today. Okay, good. Okay, which is inconsistent with what was left, but that's okay. Okay, let us continue with our great work on a review of some of the different aspects of probability and random processes that we talked about. I believe that we ended last time. Did we end with the ageless exponential? Let's see, I think we did talk about the Cauchy random variable.
The mixed random variable.
The mixed random variable was the last one. Okay, thank you. In that case, if it was the mixed random variables, then we should go to... okay. So we go to the next page, which continues the review of probability and random processes. We're going to slow down just a little bit here today because we're going to be talking about transformations on a random variable. Transformations on a random variable means as follows. Many times we know a random variable and its underlying probability density function, but we're not interested in that random variable per se. We might measure a pressure, for example, and instead of doing the pressure, we divide by some reference pressure, and we take the logarithm of that to get a dB sort of reading. So the question is, if the original pressure, for example, followed a Rayleigh random variable, and we divide it by another pressure and take the log of it, what is that new random variable? Clearly it is a new random variable that we have. What is the density function of that new random variable? Another example which I gave previously was that of measuring power across the 1 ohm resistor. If we know, for example, that the current going through it is a noise source with a Gaussian probability density function, and that the power is equal to the square of the current, given that the current has a density function which is a Gaussian, what is the probability density function of the power? So these are the sorts of questions that we are going to address on transformations of a random variable. This ideally is included in the prerequisites for the course, but my experience says that most people haven't had it before, so we're going to slow down a little bit as we describe it. So here is the problem. Here is the problem that we had. I looked at the streaming video. How many have looked at the streaming video? One person, okay, two people, okay, that's good. And I found out that the pen was the best pointer. If I use my finger, it looks kind of stupid. So a pen, we need something with a little bit more authority than a pointing finger. So here is the general problem of a transformation on a random variable. Could we get the title on the screen, please? Thank you. Transformation on a random variable. Here is the problem. We are given a density function, f sub x of x, corresponding to a description of a random variable, and then y is equal to g of x. Now, g is an arbitrary memoryless function. That's a fancy way of saying that it's like e to the x, log of x, cosine of x, hyperbolic cosine of e to the x, cosine sine of cosine of x. It's any function of x that we can imagine. So we are given the density function, and we are given the transformation y is equal to g of x. For the power example problem, g would be equal to x squared. G of x would be equal to x squared. In the dB example, it would be equal to something like a logarithm. So the problem is given the density function of x, we are to find the density function for y. So the problem is, given f sub x, which is the density function for x, and this transformation rule, find the density function for y. You'll notice this is not necessarily a misprint. This is f sub y of x. The random variable actually can be a function of anything you want it to be. We usually have it the lowercase of whatever the uppercase random variable is, but there's really no necessity of it. Now, I'm going to give you the example. When you look at the example, it should be opaque to you if you have not seen this before. You'll look at the result and you'll go, I don't understand that. And if you haven't seen it before, you shouldn't understand that. But this is essentially what we will be showing after we go down a path of explanation. The problem is determined by doing the following. We solve the roots of y is equal to g of x. In other words, if you look at the function y is equal to g of x, there are certain places where this is going to have roots. And we look at the roots of y is equal to g of x, and we call them x sub. This was a Greek letter when I did it initially. I think if you look in the slides, it's a Greek letter. The version of MATLAB that is, not MATLAB, but the version of PowerPoint that is being used here is an older version which clearly cannot revert to the font that I used, so we'll have to live with the fonts that he gives us. So this is x plus star, where star is equal to 1 through n. And then the transformation is that the density function is equal to the summation over all these starred values of the density function divided by the magnitude of the derivative at the root point. Now again, if you look at that, you should go, I don't know what that means. That's okay, because that's something that we are going to explain. Now we're going to look specifically at the case where y is equal to g of x, and g of x is strictly increasing. So therefore g of x could be something like a log. It could be something like could it be x squared? Well, x squared is not strictly increasing, is it? It's not strictly increasing because it's more of a bowl. However, if the random variable to begin with is positive, then x squared is strictly increasing. In other words, if the only outcome for the random variable x I have is positive, then for positive values of x, isn't x squared strictly increasing if we restrict ourselves to positive values? The answer is yes. So we can't. But if we talk about a random variable that takes on both negative and positive values, it is not strictly increasing. E to the x is a strictly increasing function. Y is equal to x cubed is a strictly increasing function. You notice that we use the word here strictly increasing because we're not allowing this thing to plateau off. It is contrast with the idea of monotonically increasing, where monotonicity says that you can actually reach a plateau and stay on that level for a while before you go up again. Strictly increasing means, oh, you move to the right, you got to move up. It can be just a little bit, but you got to move up. So one of the nice things about a strictly increasing function, y is equal to g of x is that inequalities are maintained. Specifically, if we have a number a which is less than b, and if g is a strictly increasing function, then a being less than b means that g of a is also less than gb. Makes a lot of sense. So if we have a here and b here between the copyright notices, we see that a goes to g of a and b goes to g of b up here. And if b is greater than a, certainly g of b is going to be greater than g of a if indeed the function is strictly increasing. And that's a property that we will use in looking at the statistics or the probability density function of what is going on. Now here's something which is very interesting. If y is equal to g of x is strictly increasing, then so is x equal to g inverse of y. What does g inverse of y mean? Let me explain this. Well, let's see if I have a picture of it. I forgot what I did here. Okay. So we have y is equal to g of x. This is a nice strictly increasing function. X down here can be thought of as g inverse of y, because we can literally take this function and we flip it on its side so that the x-axis here now goes up and the y-axis here goes to the right. And we have made now another strictly increasing function. Xg inverse of y is known as the inverse of this original function. If we have an e to the x, what's the inverse of e to the x? A logarithm. Because if we take the log of e to the x, we get back the same thing. And indeed, if you take e to the x, maybe this would be a good place to draw a picture. So if we have y is equal to e to the x, where this is x, and of course e to the x goes like this, a very nice strictly increasing function. If we look at, and it keeps on going this way, and then we flip this around so that now we have x here is equal to g inverse of y. Well, g inverse of y corresponds to actually flipping this around one way and then another way, and g inverse of y looks like this, which is exactly this curve kind of transposed and flipped around, right? And this, of course, is equal to the log of y. And you know that you have an inverse function. When you operate on the function by its inverse, you come up with an identity. In other words, g of g inverse of y is equal to y, because we know that e raised to the log of y is equal to y, for example, correct? So therefore, we're generalizing this concept. Instead of talking about specific functions, we're recognizing anytime we have a strictly increasing function, we also have a strictly increasing inverse, and that strictly increasing on one implies that the other one is also strictly increasing. So that's the point that we're making here. And here at the bottom is the example that I just gave of y is equal to e to the x equal to g to the x. Then x is equal to the g inverse, which is the logarithm. Let's look at the case when y is equal to g of x is strictly increasing. So this would be e to the x, logarithm, whatever. We start out, remember what we're doing, it's the random variable y is equal to the function g operating on the random variable x. We know the density function of x, we want to find the density function of y. Or equivalently, the distribution function of y, because if we find the distribution function of y, we can differentiate and find the density function of x. So we start out with actually what we would like to determine. We would like to determine the distribution function of y. So we begin by writing this as equal to the probability that the random variable y is less than or equal to y. This is indeed the definition of the cumulative distribution function for the random variable y. At this point, we can say, well, what is y equal to? That's equal to g of x. So from this first step to the second step is just substituting the value y is equal to g of x. The random variable y is equal to the function g operating on the random variable x. Now we're going to take advantage of the strictly increasing nature of the function. Remember, if the original function is strictly increasing, then the inverse is also strictly increasing. We illustrated that. So what I'm going to do now is I'm going to operate on both sides here by G inverse. So on the left side, it's G inverse of all of this. On the right side, it's G inverse of y. So this would be like raising both sides to e to the x, or taking the logarithm of both sides. And again, because it's strictly increasing, what do I know about the inequality? The inequality stays because of the strictly increasing nature of the function. So that's the key right here as to why I required things to be strictly increasing. It's because I want to maintain this inequality. And this only holds in this case when G inverse is a strictly increasing function. Well, now I can take advantage of the fact that if I do an inverse on the forward function, that becomes an identity. So G inverse on G of x is equal to x. That's like the log of e to the x, or e to the log of x. If you do it, you obtain the original x back. So all of this stuff on the left simply becomes x. Yes?
It seems like since you're using less than or equals, that it would be okay to have a little plateau.
I will show you later why you can't.
Okay.
A quick explanation: if you do have a plateau, then it turns out that your random variable that you're transforming to becomes a discrete random variable, and you have to be very careful about the way you treat it. So we will address that. For now, it's strictly increasing. So we now have the probability that y is less than or equal to G inverse of y, which is f sub x of G inverse of y. What does that mean? Well, that means in the definition of what we were doing is that f sub x of x is equal to the probability that x is less than or equal to x. Well, there's nothing magic about this definition. We could have f sub x, since we're dealing with strange PowerPoint fonts, of a smiley face. That's the probability that x is less than or equal to a smiley face. It doesn't matter what is in this point as long as whatever is here we put here also. This is just a dummy variable that we use to for bookkeeping to say this value is reflected over here at this value. Okay? With that in mind, if we go back to this definition, we have the probability that x is less than or equal to, well, this is the smiley face, right? So it's f sub x of whatever this is, so it's f sub x of G inverse of y. And this is a very useful result, because this tells us the distribution function of y given the distribution function of x, which is what we set out to do. So we have a transformation that we can use for strictly increasing functions. Many times, however, we don't want the distribution. Rather, we would like to have the probability density function, which we obtain by performing a derivative of this, of the distribution function. So here's the result. The last equation on the previous slide, f sub y of y is equal to f sub x of the inverse function. Now, in order to get the density function here, we have to differentiate with respect to y. So this means doing this. If we substitute in the value of x, we need to differentiate with respect to y here. At this point, we use the chain rule of differentiation. I hope you remember the chain rule from calculus. You're going to be using lots of differential and integral calculus in here, by the way. And the derivative of y with respect to this is equal to, by the chain rule, the derivative of the argument, so it's the derivative of the inverse, times the derivative f sub x prime evaluated at the inverse. So this, again, is obtained using the chain rule of differentiation. There was a question I saw somewhere. No, must have answered it. So here is actually your equation. The density function of y, given g of x, we can compute the density function, given the density function of x, and given the transformation g of x is equal to y, we can compute the density function for y according to this formula. So if you give me a density function for x, be it a Gaussian, Cauchy, whatever, I can substitute in here and obtain my result. Now here's something which is interesting. You'll notice in this formula that we actually use the inverse, the derivative of the inverse, that is dg inverse of y dy. It turns out, and I'm going to illustrate this in a minute, that's the same thing as 1 over the derivative of g. That the derivative of the inverse is equal to 1 over the derivative of the original function. Let me illustrate this. We have a function here, x is equal to g inverse, and it has a slope at some point. Now this slope, of course, is the rise over the run. So if we have x here, and we have g inverse of x, then the slope, or the derivative of this point, is going to be equal to the distance of this leg of the triangle divided by this distance, correct? Now let's look at just the geometry of the original function. The original function is obtained by taking this and rearranging it by flipping and obtaining the original forward function. Now the original forward function has, at the same exact point, I'm using the same exact point on both of these cases. Now over here, the derivative is rise over run, so it's the small leg divided by the long leg. Here, it's the exact opposite. It's the long leg divided by the short leg, correct? So they're reciprocals of each other. The derivative here is equal to 1 over the derivative here, just by looking at the triangles of what goes on. It isn't a proof, but it's an illustration indeed that's the case. So this is a nice relationship to be able to use, that the derivative of the inverse is equal to the reciprocal of the derivative of the original function. And you see that by the original triangles that exist there? So we can actually use this in our previous formula. Remember our previous formula had this dg inverse dy? We can actually now reciprocate it and just make it a function of x if we so desire. So, making the substitution, recognizing the reciprocal relationship, I'm going to redefine the transformation. It's equal to f sub x of x divided by dg of x dx. Don't forget that x is equal to dg inverse of y. Okay, and that's the definition that we're using. So I've used this reciprocal relationship in the definition here. So this, again, is only valid when the original nonlinearity is strictly increasing. We could go through a similar derivation, I think you could see, without too much imagination, for a function being strictly decreasing. And we would come up with very similar results. Now, if you have a function which is strictly decreasing and you have an inequality, you operate on both sides by the function that's strictly decreasing, what happens to the inequality? It flips now, doesn't it? Right? Because the strictly decreasing flips it. So we can go through exactly the same derivation that we did before. If we did that, and we're not going to do that because the steps are very similar to what we went through, but if we did that and we compared the strictly increasing and strictly decreasing, we would find out that we could combine both of these solutions into a single solution. This single solution being the one given at the bottom of the slide here. You'll notice that the only difference between this, which is the strictly increasing, and this, which is the strictly increasing or strictly decreasing, is that there's a magnitude along the derivative. That's all. So here's a formula that we can use if the nonlinearity that we're talking about, the g of x that we're talking about, is either strictly increasing or strictly decreasing. A very powerful and very useful device. We will also find out that in general, if we don't have a strictly increasing function, we can always take whatever function we have and we can divide it up into little monotonic hunks, can't we? Little monotonic pieces, and put things together. We'll go through that in detail, and actually what we get is a summation of this, one for each monotonic hunk, monotonic interval. Does that make sense, at least conceptually, without understanding the details? And that indeed is the way that we're going to look at it. Here is the more general solution, and the more general solution actually follows immediately from the strictly increasing function. Before we get to this, let me just give you an example of a case. Suppose we have an exponential. You caught what I had last week. We have an exponential random variable. Let's subject this now to a nonlinearity. Let us subject it to the nonlinearity. I don't know, what do you want to do? Y is equal to I want to do something different. I just thought of a more fun example. You like to have fun, don't you? That's a nice, interesting unit random variable. This is the sort of thing that you generate on C Code or MATLAB when you generate a uniform random variable between the interval of 0 and 1. That's what you generate. Now, suppose you did this in MATLAB. You generated one of these, and now what you did in MATLAB after you generated one of these, what was it? X is equal to the rand. I think that probably does it. So X is equal to rand, so here's your random variable. Now what you're going to do in your next step is you're going to do Y is equal to 1 over X. You're going to take whatever random variable and you're going to perform a reciprocal of that random variable in MATLAB and generate a new random variable, Y, which is equal to the reciprocal of the original random variable. The question before the House is, given the density function of X, which we know is uniform in MATLAB, given that this is the function that you are operating on, this is the nonlinearity, what is the density function of Y? What's the density function of Y? To do that, we recognize that Y is equal to 1 over X, at least for positive values, is a strictly increasing or a strictly decreasing function. So if we have X and Y is equal to G of X, we notice that it's a strictly decreasing function. Therefore, it is one to which we can apply the general formula that we derived. Okay? The formula that we derived was f sub y of y is equal to f sub x of g inverse of y times dg inverse of y dy. That's the formula that we're going to use here. Okay, let's take a look at this problem. Y is equal to g of x is equal to 1 over x. Then if we solve for x, we get x is equal to 1 over y, and this becomes the g inverse of x, which makes sense. Little sanity check. If we take g operating on g inverse, we should get the same thing. Well, if you take the reciprocal of a reciprocal, you get back what you started from. So certainly this matches what we would like to have. Okay, with this in mind, this is g inverse of y. It's a function of y. X is equal to g inverse of y. Now, for our case, what I wrote down here was for the strictly increasing. If we want either the strictly increasing or decreasing, we simply have to put the magnitude on the derivative, as we've shown. So let's take a look at this. What is dg inverse of y dy? Well, it's equal to, if we take the magnitude, it's 1 over y squared, correct? You agree with that? Right? Please say right. Okay, good. Thank you. I don't want to have these nightmares that you don't remember differentiating 1 over y. Okay, so this is the case. So we're half done because we have this component. Now we have to figure out what this component is. Okay? Now to figure out this component, we need to first of all write down the original definition of the density function. This is equal to 1 for x between 0 and 1. and it's equal to 0 otherwise. That's not what we want, though. We want f sub x of g inverse of y. Well, what does this mean? It turns out our g inverse of y is 1 over y, but before we even get more specific, what does this mean? What I'm going to show you here is going to be valuable in evaluating functions of this sort, where there's actually unit steps or window functions chopping out portions of the function. This is equal to 1. What this means is that we take this expression, everywhere there's an x, we put a g inverse of y. That's all it means. So I've simply copied down the expression. And now we have to evaluate what that expression means. F sub x of 1 over y, which is what the g inverse of y is equal to 1 for 1 over y between 0 and 1, and it's equal to 0 otherwise. So it's equal to 1. Okay, we reciprocate. Of course, when we reciprocate, we flip the inequalities, and we get this as between 1 and infinity and equal to 0 otherwise. And this makes sense if you think about it. We've gone through math kind of opaquely, but think about it. You take a number between 0 and 1 and you reciprocate it, you're going to get a number between 1 and infinity, aren't you? Right? Take a number between 0 and 1, reciprocate it, you're going to get a number between 1 and infinity, which is exactly what was shown. So indeed, this salves our intuition. Therefore, we have f sub y, substituting into the original formula, is equal to this expression, which is nothing more than a unit step. This whole thing can be written as a unit step y minus 1. It's a unit step starting at 1 and then going to infinity, right? And then on the other hand, we have a 1 over y squared for the derivative, and that's the answer. That's what happens if you take a random number generated between 0 and 1, you take the reciprocal of it. This is the density function of the reciprocal. So it's a function which looks like a 1 over y squared. So it kind of looks like this. But it actually starts at y is equal to 1, so the actual density looks something like this. Okay? Let me do one other one. This is interesting. Same exact problem, except now we have a Cauchy. So always, as I mentioned, you always have to be careful, not careful, but you expect interesting things out of Cauchy random variables. Now the Cauchy random variable has a density function equal to 1 over x squared plus some value a squared, and then there's a constant up here. I forgot what the constant is. Anybody have their notes to what the Cauchy is?
What's the probability density?
The probability density, yes.
It's 1 over pi times the fraction of b over quantity x minus a squared plus b squared.
Okay. I'm going to center the Cauchy at the origin by taking away the a. So this is the result that we have. So this is a Cauchy random variable with the parameter of b. And if we go through everything, all of the math here is exactly the same, except the only thing that is different is, oh, I can't do the 1 over y, can I? Okay, let me tell you what I did. I goofed, because 1 over y is not strictly increasing anymore, is it? Okay? I cannot proceed with this problem using the tools that I have because the Cauchy random variable goes between minus infinity and infinity, and if I'm concerned about that, my 1 over x going from minus infinity to infinity is something which is no longer strictly increasing, is it? The difference before with the uniform random variable is I was restricted to positive values, and if we restrict ourselves to positive values, then I have a strictly decreasing function, but I don't anymore. So in essence, I don't have the tools to do this. So I'm going to backtrack and not do this problem. We're going to go now towards the more general way of finding transformations on random variables, which will allow us to do problems of this sort. Here's the basic idea. Let's go to the overhead, please. Given f of x and y is equal to g of x, find the density function of y. It's the same exact problem we had before. Previously, we placed constraints on our nonlinearity g of x. Now we're going to place no constraints on it other than it be a continuous function. What we are going to do is we are going to, first of all, solve the roots for this. What do I mean by the roots of this? Well, here's the function g of x. For every value of y, there are specific values of x which solve the nonlinear equation y is equal to g of x. So here is g of x, and if y is this value, then the roots for this value of y are equal to the values of x obtained by extending a horizontal line across here and looking at the intersections with the curve. So in this particular case, assuming g of x keeps on going up here, we have three roots. We have x1, we have x2, and we have x3. What we would do in such cases to get the density function for y is that we would sum up these values corresponding to each one of the corresponding strictly increasing or strictly decreasing functions. So we get one for each. You'll notice that this has as a special case when g of x is strictly increasing. If g of x is strictly increasing, how many of these roots do we have? One, right? If g of x is strictly increasing, we have one root. There's only one term to this, and we get exactly the term that we had back here. So we only have one term. The same is true if it is decreasing. Now, if you look at this, you might say, gee, I still don't understand it. We're going to try to explain it to you in terms of what goes on. There is a concept here of probability mass, and we're going to be talking about mappings of probability mass. Here is the idea. I'm going to draw my nonlinear function g of x here. Then at the bottom, parallel to the x-axis, I'm going to write my density function for x. You with me? That's my density function for x. And you'll notice the x-axis here is the same as an x-axis here. Over here, I'm going to write my y-axis, but I'm going to write my y-axis parallel to this y-axis. So I'm actually going to plot here my density function for y, but I'm kind of printing it sideways. I'm turning that function 90 degrees so that I can align the y-axis. The transformation on a random variable is much like that through a nonlinear transfer function that you would use in amplifier analysis, for example. And the following happens. If we have a little bit of mass here, by the way, the total probability mass is always equal to 1. So we have a little bit of mass here. This mass is going to come up, bump against the nonlinearity, and be mapped to over here. See that? And if we take this actually as a very small value and we increment it, we do little pieces of probability mass, this totally defines the mapping of the probability mass. This requires some elaboration. I'm going to redraw something similar to the figure that we had up on the screen. Glad about my own. What am I, 0 for 3? I think. So here I have my y is equal to g of x. Here is x, here is y. Here's my probability density function for x. So I have my probability density function for x here. In a similar fashion, sideways over here, I'm going to draw my density function for y. And the reason I did this is I want this y-axis to be parallel with this one, and I want this x-axis to be parallel with this one. So that's what I've done. Now, the problem is, here is illustrated in geometric form. I'm giving this density, I'm given this nonlinearity. What's my density function here for y? That's the general problem posed by a transformation on the random variable. Let's look at this in terms of probability mass. Let's suppose that I took a little bit of probability mass here between some value of x and x plus dx. Now, this probability mass has a certain interval here, which is going to map up here. And you'll notice that the slope here is very shallow. I did this on purpose because this large interval is going to map here to a very small interval on y. Do you agree with that? So this will kind of like be a y and a y plus dy. But the amount of mass that is transferred must be the same. In other words, whatever mass that I put here must be the same mass that I put here. Now, if this is a large interval, and I have an amount of mass here, and this is a small interval, what can you say about the tube that I have to fill up in order to have the same mass here? It has to be a lot larger, doesn't it, in order to have the same exact area, correct? So the amount of value that I have to fill up here has to be quite a bit more. And indeed, if this is f sub x of x, which it is, for small values, we can treat this as a rectangle, which has a height of f sub x of x, whatever that value of x is. And we can treat this as the corresponding f sub y of y. And we know that f sub y of y times dy, what is that equal to? That's equal to the probability of the mass that's in here, right? In other words, the height of the density function here, if we did this for all of the values, we would actually map out a density function here. It's the height of this density function times the width, the little skinny rectangle, right? And the mass, the total mass in this area, probability mass in this area, has to be exactly the same as here. Because once we're done, all of the mass here, which is a mass of 1, has to map here. So we have kind of a law of conservation of probability mass. So this has to be equal to the value of the function here, which is f sub x of x times dx. And here you actually have the derivation of what we took a little bit more time to do. F sub y of y, at least for this region, is equal to f sub x of x. Well, let's do it divided by dy dx. And what is y equal to? Isn't y equal to g of x by this expression? Y is equal to g of x by that expression. So we have derived exactly the same thing, kind of in a geometrical motivation, by looking at the mapping from here to this point. Now, what determines whether the height here is greater or lower than the height here? When will the height here be the same as the height here? When the slope here is 1, right? when you have a 45-degree line. If it's very shallow, what's going to happen is that this probability mass is going to have to be squeezed here, and therefore it's going to have to puff up in order to have a total composite area, right? So we must have that. So are you with me to here as far as the geometry? Notice that I've done things strictly increasing here. What happens if it's decreasing on the interval that I examine? Let me go over very carefully the next step of what happens there. We'll run a little bit over, but I haven't forgotten your break, but we're on a roll, so we don't want to mess things up here. Here is another one, another nonlinearity. This one I've chosen to be a bowl, not strictly decreasing or increasing. Here's my density function for x. And here's my density function for y. And I don't know what it is. It's my density function for y. Again, the problem. Given the density function for x and this nonlinearity, find the density function for y. This is the entire concept of the transformation on the random variable. Well, let's take the case very similar to before, where we have a little square here, and we're assuming we're x and x plus dx, so that the top value here is f sub x of x. So the total probability mass here is equal to the density function here times dx. And this must map correspondingly up to here. So we go up here, and it looks like it's squeezed down a little bit. But notice there's a flipping over of the if x maps to y, and x plus dx maps to y plus dy, there's a flip. The y plus dy comes before the y, right? So it's like integrating from big values to little values now, which corresponds to a negative sign. But as before, we must choose the height of this, whatever it is, we must choose the height of this to be such that the total area here, f sub y of y is f sub y of y times dy. Actually, this is actually times minus dy now, isn't it? Since we have a reversal here. So f sub y times minus dy is equal to f sub x times dx. So we have a minus derivative, but the slope's negative. So if it's negative, the minus of a slope that's negative, same thing as the absolute value. Okay, so this allows us, for both strictly increasing and strictly decreasing, to impose the absolute value. So f sub y of y is equal to f sub x of x divided by dy dx, and now we have a magnitude here, where y, of course, is equal to g of x. But there's something interesting here, I think you can see. And that interesting thing is, not only does the probability mass here map to this point, but there's a probability mass over here. Isn't it true that the probability mass here will also map to that same exact interval? Correct? So we actually need to do a superposition. We need to take this probability mass, map it here, then take this probability mass, map it over here, and simply add the two. Therefore, let us be a little bit more exacting. Let's call this x1, and let's call this x2. And in a similar fashion, we have a mapping over here. Now, the mapping is going to be exactly the same formula here, except that the x's are different. In one case, we're going to have x1. In the other case, we're going to have the mapping due to x2. Correct? And I think at this point you can see the generalization. If, for this value of y, we cut through the function n times, then we need to do n of these mappings over here to accumulate the value of the density function at this point in order to generate that density function. Okay? This then is the explanation for the formula which I have on the screen. If we could take a look at that, please. This is the formula that we have simply derived, that the density function for y is equal to the summation over all n of the values corresponding to all of the cuts for that value of y of the value of the function divided by the magnitude of the derivative. So what we're doing here, what we see that we're doing here, as we've just explained, is we've taken the probability mass of the density function here, mapped it to y. We've taken the probability density of the x here, and we've mapped it to y, and done exactly the same thing for x sub 3. And we do that for all of the different values of x's that we need to do. So this is a very useful, very general formula for a transformation on a random variable. I don't know if you've noticed it ever before in your work, but you ever notice the more general a solution is, the more cumbersome it is to use? That's a rule of thumb, and it really is. It's a very general formula. However, we're going to take our break, and when we come back, we will see that there's some transformations that one can do just by your intuition. And when one gets very good with these transformations, there are simple transformations which you can do almost in your head. And we'll look at a few of those. Let's go ahead and have the break and meet back here so we can dismiss early when the big hand's on the 7. Any questions before we dismiss? By the way, one thing I would really appreciate, and I think I mentioned it the first day, it's very disruptive if before I dismiss you, you start getting up and moving. Nobody pays attention to me and it hurts my feelings. Okay? So what I would like you to do is wait till I dismiss you before you start rustling and get up. And if you do that for me, I'll make sure you get out of here on time and you're dismissed on time every time. Deal? Okay, you're dismissed. Big hand on the 7. Thanks. I turn around and I'm on. Okay, let's go to the, there I am again. I want to go to the overhead. I wanted to show you something about adult math tables. We talked in here briefly about gamma functions and such. If you are going to be messing around with higher transcendental functions, these are functions which cannot be defined by elementary functions. For example, the error function. It's the integral of the Gaussian. Well, there's no way we can express that in terms of e to the x's or logarithms, so we have to make up a new function. Most of the higher transcendental functions were derived by solving differential equations motivated by physics. There are two classical adult math tables. They're adult in the sense that they are the only two that I've ever seen referenced in the literature. If you are interested in having one of these, a math table for your library, please use one of these. Don't buy Shams outline or CRC or those other ones. Those are for immature engineers. These are the adult ones. And they're essentially classics in their field. What is interesting is that higher transcendental functions have fallen out of favor. Anybody know why? Because we have computers now, and we don't have to rely as much on analytic techniques as we did, say, 50 years ago. So, no, I'm not that old. But we don't have to rely on them as we did then, because if we have a differential equation, we are not stuck with sitting it down and working out with a pencil. Rather, we can go to the computer and solve it with finite element analysis or some other numerical analysis sort of technique. So in some sense, the use of higher transcendental functions is fading, yet they still exist and are used in engineering. We have come across them in here in terms of the gamma function. These are functions which we can't get around using. They're so useful. Imagine getting around in life without using a sine or a cosine, right? That would be very rough. There are other ones which are, it'd be hard. It'd be a hard life, right? But you could do it. You could do it. And so there's two books. One was actually done many, many years ago. It's a very old book, and it's the Handbook of Mathematical Functions with Formulas, Graphs, and Mathematical Tables, affectionately known by the editors Abramowitz and Stagun. It was put together by the National Bureau of Standards way back in the Middle Ages. It actually contains tables of different things, which aren't very useful these days because we can get table values very, very quickly. Nevertheless, their treatment of higher transcendental functions in terms of the relationships, the definitions, the graph, and the visualization of them is very useful. The second one is probably a more serious book by some Russians that was actually penned when the Iron Curtain was up, Gradstein and Ryzhek, and you can't see it here. It's called The Table of Integrals, Series, and Products by Gradstein and Ryzhek. And it has no pictures in it. It's just page after page of relationships for integrals and such. And it could be that some of the symbolic math packages are sophisticated enough to have incorporated some of the results of Gradstein and Ryzhek. I don't know. I haven't looked at the symbolic math programs as of late. But these are the results that you should get. So either one of these is the book that you should get. It is not required for this course. I will give you all of the information that you need to know about higher transcendental functions if we deal with them. We've already seen a Bessel function, we've seen a gamma function, and an error function. Those are all higher transcendental functions, each of which are chapters in this book. So I thought I would tell you about that. And by the way, there's a question. When people initially see higher transcendental functions, there's initially a feeling of, oh my goodness, I don't understand that. But in fact, you do. You just don't know that you do. For example, if I ask you, do you feel comfortable with sines and cosines, your answer would be yes. Yet I would ask you, what's the cosine of 15 degrees? You probably couldn't give it to me with one figure of accuracy, could you? I couldn't. So why do you feel comfortable with sines and cosines when you don't even know what the sine of 15 degrees is? Do you? I maybe think about it a little bit. I don't. The reason you feel comfortable with sines and cosines is that you know a few rules to manipulate them. You know how to differentiate them. You know how to integrate them, number one. Number two is you know kind of what they look like, right? They're bumpy things, and they go up and down. Seriously, so you visualize this when you write down cosine, you visualize a cosine. So, number one, you know rules by which to manipulate them. Number two, you kind of know what they look like. And number three, if you needed the sine or cosine of 15 degrees, you would know where to go to find it. And it's the same with all of the transcendental functions. If you know those three things, that's all you really need to know in order to be as expert in those as you are in sines and cosines. You need to know, number one, rules by which to manipulate them. Number two, kind of what they look like. And number three, where if you need to find the values of them, you know a place to go to get them. And that way you can learn the higher transcendental functions very, very quickly, and it shouldn't be that much of a problem. So that's my little do not be afraid of higher transcendental functions talk. Okay, let's return then to the lectures after having Okay, my computer is... The mouse doesn't work, and this mouse... Oh, there it works. Okay. Okay, I want to return to this slide here, which is the mapping, to reiterate exactly what we're doing in this much more general case in terms of mapping probability masses. Now, with this, let's talk about a question which was raised previously. What happens if we don't have a derivative? What happens if, well, we do have a derivative. Suppose that the nonlinearity flattens out. What happens there? It turns out something very special happens at the point where the derivative flattens out. And I'd like to talk about that right now. Let's draw exactly the same sort of y is equal to g of x curve as we had before. Except now what we're going to do is we're going to let this nonlinearity flatten out. Thus far we have assumed that it was a strictly increasing or strictly decreasing function. And so it increases. What to do when your nonlinearity is flat. Here as before is our probability density function, f sub x of x versus x. Now maybe, from what you've seen thus far, you can tell me what happens. Anybody have an idea? That hasn't seen it before. If you've seen it before, it's not fair. Anybody have an idea?
Impulse.
Yeah, an impulse. Why? What happens?
Well, because there's a non-zero probability that it'll be exactly that value on the y.
Yeah, that's exactly right. All of these points here, this entire probability mass is going to map to a single point, isn't it? All of this interval, if we look at this mapping, all of this interval maps to a single point over here, whatever this is, right? So if mass maps to a point, we have a point map, or equivalently a Dirac delta, if you will. So we have a del, and let's suppose it maps here to a value of a. So it's a del of y minus a. And what is the coefficient in front of it? Well, it's whatever mass is associated with this value. If we come down here and we take this area, let's just call this A for area here. That area corresponds to the probability mass in that interval. We find out that this is the area, the mass, which must be conserved. And so the coefficient here is whatever that area is, because all of that area maps to that single point, that single probability mass. Okay? So this is what happens when we have things which level off. Question?
So you map the rest of it around, it comes up and there's a discontinuity in our new
Exactly. In other words, you would map this the exact same way that we did with the continuous function before. And we would probably get a density function which looked like this. I don't know exactly what it would look like. And then over here we have a strictly increasing thing, so we would have something which would go like this. So you can see, in the sense that we have a delta function and we have a continuous part, that the overall composite density function is a mixed random variable. It has a discrete component and it has a continuous component, okay, in general. So that's what happens when we level off in terms of the mapping. You'll notice that mapping of this sort occurs when we perform rounding operations or truncation operations. If, for example, you had a density function and you were to take each number and you were to operate on it by, I'm trying to think of a MATLAB, a floor operation. What the floor operation is what? You take all of the fractional part and throw it away and keep the integer part. It is a truncation error. So everything between 0 and 1 would go to 1. Everything between 1 and 2 would go to 2. Between 2 and 3 would go to 3. 3 and 4 would go to 4, etc. So we get a staircase sort of thing for the floor function. And you can see exactly what happens here. What happens is that if we have this as our density function, we perform probability mass mappings. We actually would take this result, whatever mass this was, and if we looked at the density function for y going this way, then all of this mass, whatever area would be here, would correspond to a mapping here. Whatever area was here would be mapped over to here, etc. So we would have a sequence of delta functions corresponding to the quantized values obtained by operating on the floor function. Now there's a whole area for data compression, for example, called vector quantization, which asks the question, if you know the densities, where would you put these quantization levels such that all of these were equally probable? In which case you could transmit, if you had a communication channel, things which were equally probable in all of the different cases and maximize your probability of successful communication. As I mentioned before, anytime you have a very general formula, the more general a formula is, typically, the harder it is to apply to the general case. It's kind of like having a crescent wrench. You can use it for lots of different jobs, but it doesn't work really good on any job. It'll work for taking your lug nuts off, or it'll work for tightening a bolt in your computer, but you know, it's not the best thing. It's better to have a very specialized tool. The problem is, if you get specialized tools, you got to have a lot of them in order to do your entire job. So we tried to, in general, compromise on this and have a little bit of both. Let's look at some simple transformations. These are transformations on a random variable, which you can kind of do on the back of an envelope and do intuitively. I'll show you the result, I'll show you the answer, and then I'll show you the intuition behind the example. One of them is transposition. Y is equal to minus x. Y is equal to minus x. So we take the random variable x, whatever it is, and we just negate it. What do you think the corresponding density function is? Can you do it in your head? If you can't, can you do it on the back of an envelope? If you had y is equal to minus x, now you got kind of a funny situation here. Once I draw it, you go, oh yeah, sure. Here's y is equal to g of x equal to minus x, which is this, right? That's what minus x looks like. Previous to this point, I've kind of drawn the nonlinearity just in the first quadrant. I'm putting all 4 quadrants here because it's going to be important to use. Now I have some sort of density function down here, which is my f of x, my density function for x. And just to make the emphasis, let me make it asymmetric so it kind of looks like this. Can you tell me what my f sub y is going to look like? My f sub y is clearly going to look something like this, right? Can't you just see that from bouncing off the line? That it's going to look like that? In other words, this little piece is going to be mapped over here, right, etc. So you notice that what happens is that in this mapping, all that we have done is we have replaced x by minus x. Well, that's what we're doing up here. Correspondingly, taking the density function and just flipping it around. That's all we've done. So f sub y of y in this case, or f sub y of x, is equal to f sub x of minus x, which corresponds to the transpose, which corresponds to simply taking the function and flipping it around, flipping it about its y-axis. Okay? So if you think about this a little bit, from the process of mapping, it should start becoming intuitive. So this is what I have in the overhead, that if we have this transposition, then indeed the mapping is f sub y of y is equal to f sub x of minus y. Don't forget, it doesn't matter what this function is. I could put, instead of a y, I could put a smiley face. That's just a dummy variable, which is a bookmark, which tells me what I'm comparing in both cases. So this could be f sub y of x, f sub y of y, f sub y of smiley face. It doesn't matter. As long as whatever is here, I have a minus that on the right side. Okay, does that make sense as a transformation and something that you might be able to do on the back of an envelope by just sketching and convincing yourself? Here's another one. Y is equal to x minus s, where s is a fixed number. What do you think happens here? Well, here's one way to think about it. It's very different than the way you've thought about it before. Y is equal to x minus s, okay? Here's f sub x. Here's f sub y of x. That's x and this is x. Okay, if x is within this region about the origin, where is y going to be? It's going to be about that, except, let me do a plus, just for fun. It's going to be exactly the same place, but around the plus s, right? In other words, the origin is redefined to be at s, if you will. Before, if something was 0, if the random variable was 0 here, for x, what would it be y? It would be s, right? So everything is just shifted down the axis. And so f sub y of x is equal to f sub x of x minus s, corresponding to shifting this to the right by a value of s. You should be able to draw the nonlinearity graph as we've been doing, the g of x, and seeing how the density function for x bounces off, and convince yourself the same result happens. This is an alternate way to think of the same thing. I think the slide, by the way, is incorrect. This should be an x plus s. So if you have them printed out, please note that. This should be an x plus s here. What about y is equal to ax, where a is a number, I don't know, like 70? Well, you think about it. Before you multiply, say x is in the range from -1 to 1. If a is 70, what's y going to be in the range of? -70 to 70, right? So it's actually going to take the result of x and the density function of x and spread it out, because the density function now has to cover more area. And the way that we spread things out is by dividing them by a. So here y is equal to a times x. So if here's the density function for x, say it's localized, and a is a big number, just for purposes of discussion. If a is a big number, then the density function for y, if x has a small dynamic range and a is 70, then y has a very large dynamic range, and therefore is spread out, much more spread out. And the way we spread things out is f sub x of x over a. You think it would be the opposite. If you divide something by a, that means that's a magnification factor. That's how much you pull it out. That's how much you stretch it out. There's a problem here, though. If we stretch it out, we better pound it down, too, because this can only have a total area of 1, right? So if we stretch it out, we've got to pound it down, too, so the result only has an area of 1. So in order to do that, we divide by the a here. So this is another one that you should be able to convince yourself of, either in a reasoning of the type that I just talked about, which is in terms of stretching it out, or by drawing the nonlinearity map and actually performing the bouncing off of the nonlinearity, the way we did it before. We can actually combine the two. If we have y is equal to ax plus b, it turns out that f sub y of y is equal to f sub x of x minus b over a, and I'll let you work that out and convince yourself of that. This combines both the shift and the scale with it. Okay? Question?
Does the side of a matter? I mean, positive and negative.
Oh, I'm assuming that's actually a good point, and I should have a 1 over a here, and if a is negative, we need to put a magnitude out here in front. Notice that this magnitude has to be a magnitude because we can't have a density function that's negative. So if a is negative, we've got to make it positive. So it's kind of a little sanity check that we have. So this is the scaling one that we just did. Let's go to the next slide. Oh, the modulus. Y is equal to the magnitude of x. This is a very interesting one. Well, I think the best way to do this is to draw the y is equal to the magnitude of x. Draw the density function somewhat skewed. These are supposedly 45-degree lines. Over here we will do the density function for y. Now I think you can see if this is a 45-degree line that the mapping from here to y is just going to be a unity mapping, right? Okay? It's going through a unit amplifier here, so we just have a unity mapping. So whatever this is over here maps exactly over here. In a similar fashion, this maps but is flipped around. This is almost like y is equal to minus x. That's a part of the y is equal to minus x curve, right? And so this part of the mass actually gets flipped. So this other portion of the mass, corresponding to the black as opposed to the red portion, actually comes out like this. So it gets flipped over. And then if we add these two up, I don't know what adding the two up would be, but we would get the f sub y of y if we were to add the two up. I'm ending my sentence with a preposition, aren't I? If we were to, is that okay to do? It used not to be okay to do. It used not to be okay to do. Sound like I'm a street guy from Cleveland, which I am. But, right, are you supposed to end your sentences with prepositions?
You're not.
You're not supposed to? Okay.
But you can.
But I know you can, but I just wondered if it was legitimate. Okay. There's an old. Have you heard the joke about the engineer asking where the English class was, and he said, "Can you?" He stopped the guy on the street and he said, "Can you tell me where the English class is at?" And the guy says, "Hey, I'm an English major. You just ended your sentence with a preposition. It's improper to end your sentences with prepositions." The guy said, "Oh, man, sorry." I said, "Can you tell me where the English class is at, you jerk?" So that's my preposition joke. Thank you for laughing. I appreciate that. Okay, do you understand this? So therefore, what f sub y of y is equal to f sub x of x, and then you chop off the positive value. That's the red portion, right? Plus, you have to take the negative part, you have to flip it around. You're taking the negative portion, you're flipping it around, and then after you've flipped it around, you've got to chop it off for negative values. So this is what the density function becomes. So geometrically, we can think of this simply as taking this portion of the curve, folding it over to the right, and then adding the two. That's what we get for the absolute value when we perform the operation of an absolute value. See that? Taking this portion and just folding it over. So this is the result that I have here for the modulus. Y is equal to the magnitude of x. Simple modulus sort of transform. And then the one that I did before, y is equal to x minus s over a. Now, the problem that we have looked at thus far is one of analysis. That is, we were given the density function for x, we were given the transformation. There's also one of synthesis. Suppose, for example, that I wanted you to generate an exponential random variable. I said, go to MATLAB and generate a bunch of exponential random variables. Well, you know how to generate Gaussians, right? That's a rand-n operation. You know how to generate uniform random variables. That's an RAND. But how would you generate an exponential random variable? Well, here we get to a synthesis problem. We know we want the density function for y to be an exponential. We know that the x is, say, uniform. So the question is, what nonlinearity do I choose to take that uniform and make it into an exponential? Do you get the problem? So therefore, the synthesis problem is, I'm going to give you the density function for y, I'm going to give you the density function for x, and I want you to tell me a nonlinearity which will map between x and y. We saw, for example, if I wanted a density function of what was it, 1 over y squared times unit step of y minus 1, I would just take the random variable and do the reciprocal of it, right? So that, in general, is the idea of the synthesis problem. There's a similar synthesis problem, which is used extensively in non-parametric statistics. That is as follows. Suppose we have a density function, and we want to transform that into a uniform density function. In other words, x is a density function, and how do we determine that density function? Well, typically with a histogram. So we have a histogram of values. Now, it turns out that if you give me an arbitrary histogram, I don't have a lot of my toolbox for arbitrary histograms. But I do have a toolbox over here where I can do lots of things with uniform random variables, because people have studied them for a long time and come up with lots of neat tests and things for them. So I can't do it for the general case, but I can do it for the uniform random variable. So what I would like to do is take my general case, and I would like to make it into a uniform random variable. If I do that, then all of a sudden I can use all these tools in my toolbox to analyze this uniform random variable. And again, this is problem used in so-called non-parametric statistics, where there is an assumption about the underlying density function. So that's a very similar problem. The problem here is, given the density function for x, given that the density function for y is uniform, what function do you have to make the transformation between the two? So therein lies the difference between analysis and the synthesis. The analysis that we've been through so far is that given f sub x and given g, we're supposed to find the density f sub y. The synthesis problems are as follows. We're given f sub x and f sub y, and we want to find g. Okay? A similar synthesis problem, a special case, is when f sub y is equal to a uniform. Special case is when f sub y is equal to uniform. Now, they're used in two different cases. In the first case, you can go to MATLAB and you can use your g in order to generate your y. In the second case, where f sub y is uniform, the reason you're doing that is to transform your random variable into a form which is suitable for analysis using a number of different operations. So this is the problem that we will tackle. Here are some interesting results, and I will state them today, and this is where we will take up the lecture when we meet a week from today. Thursday is off. When x is uniform, for example, if we have y is equal to log of x, we get an exponential random variable. So here's your result. If we have an exponential random variable, and you want to get an exponential random variable from a uniform random variable, then you just take the log of it. Y is equal to tangent of x gives a Cauchy. Now, what's interesting is that both of these turn out to be inverse operations of the cumulative distribution function, as we will see next time. One thing I want to leave you with, and this will take the final 4 minutes of the lecture, is that the mappings in the synthesis problems are not unique. The mappings in the synthesis problems are not unique. If I want to get from one density to another one, there exists a number of different, probably an Aleph 2 infinity of different nonlinearities that I can use in order to get from one to the other. Do I want to go down that sidetrack? I guess I said it. There's George Cantor, who is the founder of set theory, also came up with the theory of infinities, saying that some infinities were bigger than other ones. And the smallest infinity is the set of countable infinity, wherein one can actually put elements in a set in a one-to-one correspondence with the counting numbers. That's countably infinite. You might have seen it before. The rationals are countably infinite, integers, etc. Then that he referred to as the number Aleph Not. It's the number after all the numbers, and then you get to infinities. Aleph is a Hebrew number, or a Hebrew letter, and it goes Aleph Not, Aleph 1, Aleph 2. So that's Aleph Not. Aleph 2, Aleph 1, you get by taking the subset, the set of all subsets of the first infinity, and that turns out to be, for example, the set of all rational numbers, the set of all points on a line, for example. I'm sorry, the set of all irrational numbers. The number of sets on points on a line. This is characterized by the fact you can't tell which point is closer to another one. If I were to give you a countably infinite set, like the set of integers, and I were to say, okay, 2, you would go, 1 and 3 are closest to that, right? But if I were to give you a number line number like pi, and I were to ask you, what is the number closest to that, you couldn't do it, right? There is no number closest to it. So that's Aleph 1. So, and then Aleph 2 is the set of all subsets of this other integer, Aleph 2 is the set of all subsets of an Aleph 1 infinity. An example of that is all of the curves that you can draw on a piece of paper, okay, on a plane. That's Aleph 2. And so my conjecture is that the number of different transformations that you can get in order to transfer one random variable to another one might be Aleph 2. It's probably Aleph 1, but it might be Aleph 2 since we're dealing with curves on a piece of paper. What's interesting is that nobody can figure out what Aleph 3 is. We can think of Aleph 2, but it's like thinking 4 dimensions. You know how you can't think in 4 dimensions? It's kind of rough, or 5 dimensions. It just goes beyond your mind. You can't think of Aleph 3. There's no examples of it. Aleph, the Hebrew number, Aleph looks kind of like an N. So that would be Aleph Not, for example.
The set of all surfaces is probably equal to Aleph 2.
No, because infinities lose your intuition. The number of points on a square is the same number of points on a line segment, right? You've seen that. So therefore, just extending dimensions doesn't help you a lot.
Exactly.
Okay, so we have to be very, very careful. So I have run out of time. I will have to wait till next time to show you why the number of hold your taters, please. Why the number of transformations for a random variable is Aleph 2. Are there any questions? Okay, thank you. You're dismissed.